Okay, so today we're going to continue and probably finish up with strings and string processing. And then if we have time at the end, I'll go ahead and show you a tool that you'll use next week in Hack 9, which is called GDB, GNU's Debugger. And you might also want to use it on your assignments going forward once you've learned gotten the hang of it. If we don't have time at the end, then I'll go ahead and save that for Thursday for a little bit, and then use the rest of, Wednesday. And then use the rest of Wednesday for going over the last semester's midterm as review and as practice for your midterm after the break when you come back on that Wednesday. What would it be? The 17th would be your midterm day. Once again, it is open book, open note required computer. So you have to have a working laptop, either your own personal one that you've checked out, because you are doing live coding exercises that you'll hand in through web hand-in. The web grader will be set up that you can run it as many times as you want within that hour and 15 minutes. If you do not have a working laptop, then you need to come to me and we'll set up an alternative. I'm going to have one GTA and one LA parked in not the resource center, but lab 15 most likely, or maybe one of the other instructional labs so that you can use a lab computer instead. But of course, those seats will be limited. And because it's going to be in the lab, if it's in the open lab, then we can't guarantee absolute silence. If it's in the instructional lab and there's not a class in there, if we can grab one, then we might be able to swing that, but we don't know yet. So if you are in need of other accommodations besides using your own personal laptop, then please make sure to let me know so we know how many to plan for. So we talked about the basics of strings last time, last Wednesday, that a string is basically a character array at the end of which you have this special character called the null terminating character. If you don't have the null terminating character at the end, then it's not a valid string, and you can get yourself into all sorts of problems when you try to go and process that string. Which brings us to the topic today. Once you've got a string, what else can you do with it? We looked at how to copy it. We looked how to iterate over the individual characters. We looked how we could concatenate it. But how can we actually play with the data that is stored in that string? Oftentimes, strings actually represent data that need to be processed. One common way of doing this is with CSV data. That's comma-separated value data. This is often called a flat file. If you've got data, say records from an Excel file where you've got rows and you've got columns, well, each line is its own row. But how is each column represented on a single row? It's usually delimited with commas. Here, if you've got, say, four columns, first name, last name, GPA, NUID, right? Then you'll have three commas in between all of those that are separating them. Now, this is formatted data. It's not necessarily structured data. Structured data is something that we'll talk about later, and which is going to be more of a topic for computer science too, when you actually start looking at relational database management systems, and using SQL and stuff like that. But for now, we'll keep it simple. We'll look at flat files and CSV formatted data. There are standard library functions that can help, but processing often involves designing algorithms for the formatting of data that you expect. All right? So to help with that, there are several more convenience functions in the standard string library and in other libraries. For example, there's a library called CTypeH, and this provides basic checks for individual characters. So you have functions like is alpha, there we go, char of C. That's going to return true or false depending on whether or not the character that you give it represents an alpha, I believe, alphanumeric character. A through Z, both capital and lowercase, and I believe 0 through 9. But to know for sure, how would we know for sure? What do we need to do? We need to RTM. Man is alpha. Right? There it is. Is alpha function test for the character for which the is upper or is lower is true. So we've got two other convenience functions there. So it's just just letters, A through Z, both capital and lowercase. So those are two more that you can add to the list. Is upper, all right, char C, and is lower, char C. So there are convenience functions that allow you to determine whether or not a particular character is a lowercase character, is an uppercase character, or is an alphabetic character to begin with. Yeah?
Can you go back to the
Okay. Yep. It's in the CType library. Yep.
Yeah, but it takes in
That's a good observation. It returns an int because it's true or false. But the input is indeed an integer. Why is it an integer? Well, it's not a character. Maybe I should go ahead and go back to the notes and change those to ints, but I want to drive home the point that you'd only want to use it for characters. Why is it defined as a character, though? What is a character? What is the character capital A? What's another way of representing that? 65, right? An integer. It's because of the ASCII text table. The ASCII it's going to just operate on the numerical values anyway. But you're right. The parameterization here is seeking an integer. What happens if you give it something that is greater than 255 beyond the ASCII text table? Who knows? Probably, this particular one is definitely going to return false because that's definitely not 65 through whatever or 10 or whatever lowercase a is through whatever, right? You also have other convenience functions. In addition to that, you have is space, right? I'll just leave it blank here, right, to not have that. Or is digit, right? You have also conversion functions. You have to upper or tupper, right? That is, you give it a character, and if it's a lowercase character, it'll return the uppercase equivalent, an integer representing the uppercase equivalent corresponding to the ASCII text value. If you give it something that's neither lowercase nor uppercase, like an exclamation point, it'll simply, I believe, return the exclamation point again. So there's also to upper. If there's to upper, there's also to lower, right, etc. Right? So you can use those for individual characters. Understand, though, they're in a different library, the CType library. You would need to include that separately. It's not in the string library because it doesn't necessarily operate on strings. You see the demarcation of responsibility here. Math stuff is in the math library. String stuff is in the string library. Character stuff is in the CType library, etc. Right? You can also format strings, formatting. Right? So in C, recall, you can print a string using printf and the placeholder. What was it again? What placeholder do you use for strings? %s, right? So that's straightforward. But here's another thing you can do. You can also print a result to a string, right? Usually when you use printf, you are printing where? To the standard output. You're printing to the screen, to the console or the terminal or whatever you want to call it. You're printing to the standard output. If you want to format a string and then store it in another string, you can do that by printing, right? You're not printing to the screen. Instead, you're printing to another string. The way that you can achieve this is you can use sprintf. So it's the same printf function, print formatted, but there's an s in front of it. What do you think that s stands for? String. String print formatted. And here to print to a string. Right? Its use is exactly the same, but there is an additional first argument, the string you want to print to. Right? Here's an example. Now, I will go ahead and declare a static string here. Again, these things are, in general, are bad to use. If you're going to just use it as a buffer, we'll talk about that later. If you're just going to use it as a buffer, it's fine, and as long as you keep it small. 100 bytes, that's nothing. How long of a string would I be able to store in that thing right there? 99, because you at least need one spot for that null terminating character. So let me go ahead and declare some variables and values here. Let me go ahead and declare an integer, a double, and another string, my name, right? Chris. Now, if I wanted to print to the standard output, I could do something like this. Printf, hello, %s to print my name, right? You have a value of %d. I'll go ahead and print out the integer here, x, and pi is equal to, I'll go ahead and go %.3f, end the line, and so I will print my name. Let's go with my name, which is name, x, and pi, right? There we go. That would print to the standard output. Let me go ahead and go to the next line here so that we can see this. There we go. There. Don't worry about going to the next line. I'm just trying to fit it up here on the screen. That's how you would print to the standard output. How would you print, say, to s instead? I don't want that printed on the screen. I want that formatted value. Hello, Chris, comma, you have a value of 10, and pi is equal to 3.14. What's the next one going to be? 2, because printf automatically rounds for you. So it'll be out to 3 values with the rounding, and then it'll end the line. If I wanted to print that instead to s, I would do something like the following. Let me go ahead and copy that. I would use sprintf. And now there's going to be a different first value, the string that you want to print to. And that's the only difference. Now what's stored in s is going to be the fully formatted string as if it were being printed out to the standard output, but instead it's being captured into that string value. I made it 100 of size 100 because that was big enough to hold what I was going to do, what I was wanting to do. I overestimated so that I didn't have to actually go through and count up the values. If you're going to do this dynamically, you might want to actually count the values. Or one trick is go ahead and print it out to a temporary static array that's big enough, and then go through and find and call strlen. How big was it actually formatted? Then create a dynamic string of that size plus 1, copy it over, and then you're good to go. And then you didn't have to do any of that low-level character counting or anything like that. Let me go ahead and grab this and put it over on REPL to show you how it works. All right? Or show it to you in action here. And increase the size. OK, it's still working. And increase the size here. There we go. Oh, well, too much. There we go. Oops. I'll put it there. All right, so I'm going to go ahead and print out the result, s. %s, I'll print s, just to show you what it looks like. Now, it's going to print this twice because it's going to print it once for line 9. Oops. It does not like the going to the next line there, probably. And, oh, where's the semicolon? Oh, thank you. There we go. There we go. Hello, Chris. You have a value of 10, and pi is equal to 3.142. And then the exact same thing, but this time, this thing is stored in s. So if you need to do formatting, and build a string somehow using the formatting, then you can do that. And instead of printing it out, you can store it in s. And then once you've got it stored in a string, you can do whatever you want with it. You can print it to a file, which is going to be one of our future topics, or you can print it to the standard output, or you can print it somewhere else. There are other places that you can print other than the standard output. Okay. Now, for the real processing here. So as I mentioned, there were many strings can be formatted either through CSV or through TSV, which is going to be tab-separated values. If you ever work in Excel and you need to dump it to a file, well, you can always save it in Excel. But if you want to try it sometime, go into Excel and save as. Then select the format. You'll see a lot of different formats. Many different Excel formats, but you also have stripped down flat file formats, which include CSV and TSV. You can save your Excel file as a CSV file. It's just going to be data, so any formatting or macros or formulas that you've put into an Excel file, they're not going to be preserved, but at least the data will be preserved. Okay? Oftentimes, you're going to want to iterate over it. So let me just give you an example here. Let's say that I've got a char s, or data, is equal to Chris, comma, Burke, comma, my NUID is 314-10602. I live in Omaha. My office is 363 Avery Hall. There we go. So there's some basic data about me. It's all separated by a comma. I've got my first name, comma, last name, comma, et cetera, et cetera. Each one of these things is called a token, right? So each individual piece of data, individual piece of data is a token, right? And what I want to do, is I want to iterate over this this data here, and I want to tokenize it, right? Tokenization is the process of iterating and processing each individual token in a formatted data string. Right? So again, I just want to go over it. Processing, I don't know what I'm going to do with it yet. So by processing, I'll just say that I'm going to print it out. I want to print out Chris, then I want to print out Burke, and then I want to print out each one of those tokens separately, one to a line, just to show you how the tokenization process works. Later on, when you actually start processing data, you'll actually want to do something with it. If it represents a balance, you'll want to add it to something. Or if each row represents an object or a person or something, you'll want to conceptually create that entity. That gets us into structures, which is going to be one of our future topics. All right? But for now, I'm just going to go ahead and print this stuff out. Okay? There we go. So to do that, there is a nice function you can use, strtoke. What do you think that stands for? String tokenization, exactly. All right, it takes two arguments. The string you want to tokenize, and a list of delimiters you want to use. All right? Generally, we'll only use one delimiter, right? Because you can have different, you can have semicolons as your delimiter instead. That each token is delimited by a semicolon, semicolon, semicolon. Or you can use, like we're going to do in this example, commas or tabs, right? Or some other token entirely, or some combination of tokens. And so generally, we're only going to use one delimiter. The first time you call strtoke, strtoke, you pass the string you want to tokenize. Each subsequent call, you pass null. And this is just a convention. strtoke doesn't know that you want to continue tokenizing the same string that you started with, or you want to start over on a new string. So the way that you tell it the difference between continue on this string or continue on this new string is by passing different parameters to it. If you pass a string for the first argument, it's going to continue processing that. It's going to start processing that string. If you pass in null, it continues processing whichever string you had before. Right? And it also, each call returns a char star pointer to the next token that you can then process. You can do whatever you want with it. Again, for our purposes, we're simply going to print it out, one to a line. Okay. So let me go ahead and go back over to REPL here. Let's get rid of this stuff. Right. There. Now, as a first try here, I'm going to call strtoke. I want to. If I'm going to use string stuff, what should I do? Include string. String.h. I should be including the standard library. It's doing it for me for some reason, but it doesn't have it. There we go. All right, let's clear that out. The first time I call it, I'm going to pass in the string that I want to tokenize, followed by the delimiter. So the delimiter that I want here is going to be a comma. I used double quotes there. That's because it actually supports a list of delimiters. If you wanted to use comma and semicolon and say tab and maybe a space, it would use all four of those things as a delimiter. If you only want one delimiter, then you use a string of size 1. It would be wrong if you used single quotes, because is that a string? Nope, that's a single character. And strtoke is expecting 2 strings. The string that you want to tokenize and the delimiter that you want to use. Okay? And again, strtoke returns a character pointer to the next token. Right? Let me go ahead and do that. And let's go ahead and printf token is equal to %s end the line token. Right? And let's run it and see if it works. There we go. There's the first token. Did it include the delimiter there? Does it include that comma? It doesn't look like it. So it takes the comma out and only gives you the token. All right, well, I want the next token. So get the next token. Right? Token is equal to another call to strtoke. Right? And what do I pass it this time? I want it to continue going with the same string that it did last time, so null, followed by the same delimiter. Each call you can change the delimiter if you really wanted to. So if you've got, say, 3 tokens that are all comma-separated values, and then you've got this other single token that represents maybe an address, and each of those each element in the address is delimited by some semicolon, then you can switch over to that formatting if you really wanted to. Let's go ahead and print it out again. And this time it should have Chris and then my last name, Burke. Yeah, works. All right. Cut, paste, cut, paste, cut, paste. Get all of them, and that should be all of them, right? What if I go one more? What do you think is going to happen here? Null. Why did it print null? What was the last token? My office number, 363 Avery Hall. So if it's done, if it has no more tokens to give, what does it return? Null. Right? That's how you know it's done. So some observations here. When there are no more tokens, strtoke returns null. Excellent. Yeah.
Since that inline character is part of the string, if like you had
I don't have an endline character up here. I only have an endline character here when I print out the token. And if I didn't have that, then it just wouldn't print out over here. Like a comma here? Good question. I believe that trailing tokens are ignored. So empty tokens are ignored. Let's find out. Yep. So an empty token at the end is ignored. What about an empty token in the middle? Let's find out. It's also ignored. So generally, empty tokens are ignored. Now, a space is not an empty token. A space is a space, and it ends up printing that. Right? So let me go ahead and end that. Was that the same question over here? OK. All right. So good questions. What about, so should I have done that? Should I have cut, paste, cut, paste, cut, paste? Probably not. Let's rewrite this. Let's rewrite this so that I'm not doing, if I added another token here, it wouldn't have, like Omaha, say Nebraska, and then this one, then it wouldn't have got now it is printing it. Well, now it's printing it, but I had one extra for the null value, right? If I only have so many print statements here, then it's not going to print all the tokens. So what kind of a structure should I use instead if I want to tokenize the entire thing from beginning all the way to the end? Probably a loop, and probably a while loop. Because unless I may or may not know how many tokens I expect up front, it could be malformed data. Say that I expect 5 tokens, but then I encounter 7. Or I only encounter 4. Right? How would I be able to handle that if I used a for loop there? I'm always expecting 5, no matter what. Right? If there's malformed data, there's no way to detect that. So let me go ahead and write a while loop. While something, continue. While I still have more tokens, print out the current token that I have. Print out the current token. And for the next iteration of this while loop, get the next token. So let's take care of this one first. How do I get the next token? Let me go increase the size a little bit. Well, we've got that down here, right? Just give me the next token. Pass in null, use the same delimiter. How do I know when I'm done? So let's get rid of all this. When strtoke returns, null. So when token is null, then I know that I'm done. So while it is not equal to null, continue to get the next token. And in this way, I'm able to get all the tokens, regardless of how many tokens I put in there. Middle name, Michael. All right, I don't know. What else? My GPA, 4.0, say, yay. Right. And now I've got an arbitrary number, or if I take out some tokens, right? Now this while loop will work no matter how many tokens I have. I could keep a separate counter. If I'm expecting 5 tokens, and I get 1, 2, 3, 4, 5 tokens, and then there's still one left over, right? Then my counter goes up to 6. I can raise an error, return an error. If I only get 4 when I expect 5, then I can raise an error, right? By keeping track of how many there are. Yeah.
What if you wanted for a token a comma?
Good question. You would not use that. You'd use something else, right? Right. Actually, in real life, CSV files are actually really complicated. They seem simple, but by going through this nice, simple example. But in real life, of course, you want a space maybe within one of your tokens. So generally, what you have to do is you have to escape it. And then you have to write your code so that you know that, oh, I should have escaped that. Because if I just go and escape this, strtoke is not going to know anything about that. In fact, I don't think this is going to compile because I'm trying to escape a comma, but a comma is not a special value, right? I'd probably end up having to do to escape the backslash, and then it'll work, but then the backslash is being treated as part of the token. So it's actually a very, very complex problem. If you're actually doing CSV file and processing in real life, bring in a library. Because it gets really complicated. Generally, if you save it in Excel, you'll see that Excel probably surrounds it with double quotes, each token with double quotes, so that you know that, oh, well, it begins with a double quote, ends with a double quote. Everything in there, including commas, is part of the token. What's the problem now? What if you want double quotes in your tokens? So it's always a chicken and an egg race, and there are ways of doing it. But they can be complicated even for simple examples. Use a library. Right? OK. So we've got that problem solved, right? For simple stuff. Right? Let me go back to the notes here and make sure that this is part of the notes so that you have it when I post this later today. Right? There you go. There's the full program. In addition, note that strtoke actually changes your string. Right? So this is something to be aware of. Let me go back and RTM, read the manual, strtoke. All right, there it is. Don't worry about restrict, char, and don't worry about strtoke. That's a reentrant version. Don't worry about that. We're not getting into multi-threaded programming here. Ignore strict for now. Char star str. What keyword is not there that we were using with respect to arrays? Const. By putting const in front of it, if there had been a const here, that would have been an advertisement that it's not going to make changes to your string. The lack of that keyword also is an advertisement. This may or may not change your string. In fact, it does change your string. Let me go back to the REPL example here, and let me try to print out data after it's all said and done. Printf, %s, or data is now equal to %s, and the line, data. Let's find out what happens here. Make sure everything's correct. Yep, good. Data is now only what? It's not the original Chris, comma, Bert, comma, ... It's now only Chris. The reason that this happens is because of how strtoke works. What it does is it just goes character by character by character and says, OK, there's a comma. There's the token that you asked me for. I'm going to change that to a null terminating character and return a pointer to the beginning of that token. Here you go. The next time you call it, where does it start? It maintained a pointer to the next one. So it'll process, sees the next comma, changes that to a null terminating string, and then returns a pointer to the second token. It's changing your stuff. It's taking out all the delimiters and changing them to all null bytes. To see that in action, let's go ahead and actually print for int I equals 0, I is less than, let's say 100, I plus, printf. Let's print out every single individual character in here. in data sub I. There we go. Probably don't need to go that high, so let's just go 50. There. So there's Chris. There's the first token. What's it printing out right here? What would be normally between there? That would be the comma. But the comma is now gone. What value is that? Let me go ahead and change it to %d to look at the ASCII text value. Capital C would be 65, 66, 67. There it is. Lowercase h would be 104. Lowercase r would be 114, ... This is the one I'm interested in here, right? 0. What's the ASCII text value corresponding to 0? The null terminating character. So it's going through your string and changing everything. If that's not what you want, what do you need to do? If you don't want your original data string changed, then you need to ... what? Make what kind of a copy? Make a deep copy. Make a deep copy of the string. And tokenize the copy. Right. Great. Good. And let's see. Comparison. OK, comparisons, and then we can do some we can either do some exercises, or I'll show you GDB. String comparisons. Comparisons. In C, you cannot ever use the equality operator on strings. Right? If you use the equality operator, what's the equality operator? Equals equals. It's not single equals. Some people are still making the mistake of putting a single equals in their if statement. And you can catch that real easy by running all of your compilation processes with wall. Wall will catch that no problem and tell you that you probably didn't mean to put an assignment operator in a conditional statement. But if you do happen to use equals equals to compare strings, it actually compares. What are you comparing? You're comparing a char star to a char star. So let me go ahead and go into code mode here and show you what I mean here. Come on. Char star A is equal to char star malloc size of char times, I don't know, 10. And char star B, we'll make that of the same size. And let's go ahead and put something in there. strcpy into A, my name, Chris. And then let's go ahead and put into B, into B the same thing. And let's ask, are they equal? If A is equal to B, then printf, come on, they are equal. They are equal. Right? I mean, conceptually they're equal. They're both going to hold the string chris, right? Otherwise, else, printf, nope, they're not equal. Predict. What's going to happen when I try to run this program? Let's go over to REPL and see. Is it going to say that they're equal, or is it going to say that they're not equal? What do you think? Flip a coin. All right. Nope. Why? A is pointing to this memory location over here. I copy chris there. B is pointing to this memory location over here, a completely different one. I'll copy chris over there. What am I comparing? I'm not comparing the contents of the string. I'm comparing pointers. I'm comparing A to B. A is a char star. B is a char star. I'm asking, are these the same memory locations? Are they? Certainly not. This one's pointing up here. This one's pointing over here. Right? So it says nope. You cannot use the equality operator to test for string equality. Prints, nope. Right? So why not? Because it actually compares memory addresses. Memory addresses. There we go. Not the contents of these strings. Well, all right, fine. Are we dead in the water here? I do want to compare strings. I want to compare apples to bananas. Apples comes first. Why? A comes before B, right? I want to compare Chris to Burke. Burke comes before Chris because B, right, comes before. I want to compare things like that. What about apple and apples? Which one of those should come first, by the way? Apples, why? Or apple, I heard, why? Because it's the shorter one, right? It matches A-P-P-L-E, but then we've got an S over here, so that comes later, right? Just like apples come before zebras. All right, so how do I do that? To make string comparisons in C, you use the strcmp function. Right? What do you think strcmp stands for or short for? String compare or comparison. Right? It takes two arguments, the strings you want to compare. And by the way, they're both consts, so they're not going to change your strings because it's just going to compare this string to this string and tell you which way they go, which one comes first. To communicate the relative order of the two strings, let me give them names, A and B. A and B. Right. Okay. Tech mode is only like that. There we go. To communicate the relative order of the two strings, strcmp returns one of three things. It returns an integer, actually, but it returns something positive if A comes before B. Right? In other words, conceptually, A is less than B, or strictly less. It returns 0 if A and B are the same string, same contents. And it returns something negative. Oh, so what? Darn it. I've got that negative. I should have gone negative first. Positive. Sorry for the formatting. There we go. And it returns something positive. There we go. Good. Something positive if B comes before A. Or another way of saying that is A comes after B, right? Or yet another way of saying that is A is greater than B, right? Conceptually. So that's how strcmp works. This pattern is very, very common. It's called a comparator pattern. Given two generic objects, do they go like this, or they're in order, or they're out of order? They go like this, or they're equal. It returns something negative if everything is okay. It returns something positive if they're out of order, and it returns 0 if they're equal. Right? It always returns an integer because you can't have, well, what is 0.5? Well, 0.5 is just positive, but when it gets truncated to an integer, it becomes 0, and that's different, right? It's showing the relative ordering of the there's only three possibilities. It goes like this, or they're equal. So it's telling you more information than what we wanted to start out with. With equals, even if that worked, it would only tell you that they're equal or that they're not equal. It wouldn't tell you that A comes before B or B comes before A. But a comparator function like this does. Technically, it's not a comparator function. We'll revisit this when we come back to searching and sorting, though. You're going to be writing your own comparator functions. So let's go ahead and take a look at an example here over on REPL. What I'm going to do is I'm going to create a result, an integer result. And I'll go ahead and call result is equal to strcmp of apple and apple. All right, there we go. And then I'll print the result. Printf result is equal to %d end the line. So what should it return here? Apple all lowercase, they're the same contents. So what should it return? It should return 0, and it does. Okay. What if I did apple and apples? You said that apple comes before apples, so these are in order, left to right. So it should return something negative, and it returns -1. Don't read anything into it being 1. It could return -10. It could return -42. It returns something negative. Don't read in anything into the magnitude of that number. What if I reversed it? What if it was apples and then apple? What should it? Now they're out of order, left to right. So what should it return? Something positive. Right? In this case, it happens to be +1. All right. Yeah, go ahead. Oh, S and S, both of them?
No.
Like that?
One, no S there.
No S there?
Yeah, and two S's there.
Oh, okay. Like 2 S's there. Okay.
Yeah, and one S.
Same up until the last?
Wait.
Wait, oh,
Yeah, one S on the first apple.
there is one S there.
Oh, I mean, no S's.
No S. Okay.
Yeah.
They're still in order, right? So it returns -1. What about comparing an apple to an apple? Are those equal? No, the cases are different. So which comes first, capital letters or lowercase letters? Capital letters? Why? ASCII text values. The capitals come all before lowercase. All it's doing is looking at the ASCII text value. It sees 65 and whatever this is, 104 or something like that, and says, oh, 65 is less than 104. So it'll return something negative because they're in order. Right? Something 0 because they're the same. But what happens if I say apple and apples? Remember, apples came last, came after apples, right? Or just a singular apple. So you'd think, well, are these in order? Or let me go ahead and change this. Put apples, there we go, and then apple, there we go. Now what's the ordering? Are they out of order because the first one is plural, or are they in order because, or are they out of order because the lowercase a there? What's this going to return? Are they in order or out of order? Out of order? Positive. Why? It doesn't matter how many characters come after. It's looking at that first character, seeing there's a difference here. 65 comes before 104, whatever it is. So it's going to say that they're out of order because capitals come before lowercase. It's not a dictionary ordering. It's something called lexicographic ordering. Lexicographic is according to the ASCII text table. In a dictionary, do you have two parts to a dictionary? All the uppercase letters followed by all the lowercase letters? No. The way that it works in a dictionary is all the A's are together, regardless of the capitalization. Then all the B's, then all the C's. You don't have two parts to the dictionary of uppercase letters and lowercase letters, right? So this is different. It's not dictionary ordering. It is lexicographic ordering. Here's another example. Apple to an orange. Apples to oranges. Right? Compare them. Which comes first? Apple, so something negative or something positive? Something negative. Right? Again, what if I go with, they're in order, so let's put them out of order by capitalizing O for orange. And now they're out of order, right? Here we go. 1,000 and 100. Or 1,005. There we go. Are those numbers? Nope. They are strings. Each number, 0 through 9, has an ASCII text value. It's not going to go through this and treat it like 1,000 versus 1,005. We will get the correct answer here, that it's they're in order, right? 1,000 comes before 1,005. But what if I do this? Which comes first, 1,000 or 100? Which one comes first? If you were to order it as numbers, then 100 would come first. So under that assumption, are they in order or out of order? They're out of order, but what happens? Well, they're out of order here. Let me go ahead and, think of another one. 20 and 100. There we go. 20 and 100. Are they in order or out of order? They're in order if you think of them as numbers, but if you think of them as ASCII text values, they are out of order. Why? It looks at those first characters, 1 and 2. Which comes first? 1. So it doesn't matter what the rest of the string is. 100 comes first. Understand that these are not numbers. They are strings. It doesn't matter what you put in them. It's going to go according to the ASCII text value in lexicographic order. If you wanted to if you wanted to compare them as far as treat them as numbers and then compare them, what do you need to do? You need to convert the strings to numbers, and you know how to do that from the first week. How do you take a string and convert it to an integer? What function do you use? How do you take an alphanumeric string and convert it to an integer? A to I. You would have to go A to I of 20 and int x is equal to, and int y is equal to A to I of 100. And now you'll get that if x is less than y, then print f in order. Right? And that will print out in order, right? Because you are comparing them as numbers. You cannot treat strings as numbers unless you convert them first. So understand that there are a lot of gotchas to that, and they can all be understood simply by looking at the ASCII text table. What does the ASCII text table say? All comparisons are according to the ASCII text table. We call this lexicographic ordering. There we go. All right. So questions so far on any of this? Yeah?
How would you compare, if you have two variables, one of them is an integer and the second one is a string?
So if you have two variables, one of them is an integer and one of them is a string,
Like, how would you compare them?
how do you compare them? How do you compare apples and oranges? What is that old saying, aphorism? What does that saying mean? You can't compare apples to oranges. So you cannot compare integers to strings.
Compare the value, but compare the types.
Oh, that's a good question. Does C have a type of? I think that you don't, because it's a statically typed language. In some dynamically typed languages, you have that problem of, here's a variable, what's its type? And so usually they support it with a type of, and then it'll give you, oh, it's a string, or it's a number, or it's something like that. In C, you don't have that, because C, it's declared. You look at the declaration. And if it's something else, then the compiler will check that. If you take an integer and try to treat it as a string, the compiler won't let you do that, because you can't compare apples to oranges. You can't compare integers to strings. Right? So it's not possible. There is another version called strcasecomp. Let me go ahead and copy that over. It tells you already that it's 0. What does it do? Let me go ahead and get rid of that. There we go. Yeah. And get rid of this. Let me see. Let's see what it prints. So we've got a mixture here, leet speak with caps and lowercase mixture, and we've got apple over here, and it becomes 0. This apple is the same thing as this apple, because we're using a different function. strcasecmp ignores the case. It treats it as if everything was uppercase or everything was lowercase, and it makes no distinction between an uppercase a or a lowercase a. They're equal in the eyes of strcasecmp. Right? And of course, there are lots of other things that you can use. You just have to read the documentation on what's available. Okay. Okay. At this point, I'm going to go ahead and switch modes here and talk about something that's a little bit ahead of schedule. Let me go ahead and get rid of this. And get rid of this too. And get rid of this. There we go. I'm going to go ahead and mark down preview plus, toggle preview, open in new window. There we go. Come on. All right. Let me go ahead and zoom in here. So something that you're going to be working with after the midterm next Thursday is GDB. GDB is a debugging tool. And now that we've gotten into arrays, many people have gotten to the point where your programs are complicated enough, they're complex enough, that it's no longer really easy to diagnose things. Way back in the beginning, if you got a segmentation fault and you were only doing printf and scanf stuff, we knew right away. You forgot your ampersand. But now that you're using malloc everywhere, that you're using maybe static arrays, you're using strings which are null terminated, which have to be null terminated. Now it gets a lot more complicated. So you can no longer, we can no longer just look at a program and say, okay, here's what's probably wrong, and you probably can't either. But you can use a tool, a debugging tool. Now, some of you have probably used the poor man's debugger up to this point. The poor man's debugging is simply just putting a bunch of print statements everywhere. What's the value of I right now? What's the value of j right now? What's the value of a sub I, j, whatever? Right? You put a bunch of print statements in there. That's not proper debugging. That's why we call it the poor man's debugger, because you can't afford a real debugger. That's not the way to go, because every time you have a bug, you put in 50 print statements. Oh, okay, now you finally figured it out. Okay, fix that. Erase all your print statements. Okay, now I have another bug. All right, put all the print statements back in, right? And as you've seen, if you do that on the web grader, it's going to dump megabytes and megabytes of print statements, and you're not going to get any results back. That's what all those PHP errors were that everybody kept seeing. You were literally printing more than 135 megabytes of output data, and because it was running a million test cases. That's not the way to go. The way to go is to use a proper debugger. A debugger is simply just a program that runs another program. It simulates that program, and it allows you to run the program, pause the program at a certain point. You can view the variable values at that pause location. You can step through line by line. Okay, you pause your program. Go to the next line. Okay, now what is the value of everything now? Go to the next line. Go to the next line. Oh, it calls a function. Jump to that function and show me what's going on. You can set breakpoints in your program and then continue the execution up to that point. So, all right, you've got on line 50 here. All right, everything looks fine here. I know that everything from line 50 down to a line 100 is okay, so I'll go ahead and set a breakpoint down here, and instead of going line, I'll resume the program until it gets here, and then it'll pause and show me what's going on. The way that you do this with C is GNU's GDB. GDB is GNU's debugger. GDB, GNU's debugger, right? And it's a command line debugger that you can use. To use it, as you will next Thursday, not this coming Thursday, but the Thursday after, you'll compile with the G flag. The G flag preserves all of the variable and function names. Because usually when you compile stuff, if you've got a function called myAwesomeFunction, right, then it's not going to use myAwesomeFunction. It's just going to compile it to a bunch of machine code. But you want to preserve that stuff because you want to look at the line numbers, you want to look at the variable names, and so using the -G adds all that metadata to your program so it can be run through a debugger. To start GDB, you simply go GDB a.out where that's your program. I'll run through all of these. Don't worry about writing them down, and I'll also post this. But let me go ahead and show you a buggy program already. Here's an array program. There we go. So here's an array program. I've got a sum function here that takes an array and sums it up of size n and sums them all up and then returns the value. I create a primes array of size 7, maybe, and I fill it 2, 3, 5, 7, 11, 13, 17. So I've got the first 7 primes. I want to sum those up. And then I print out the total. Okay? There's the sum function. It purportedly sums them all up. Now, if you saw the bugs already, no spoilers. Right? I'm going to go ahead and compile with the G flag array program.c. Right? Compiles fine. If I run it though, I get a total of 7. Right? What is that? So what are the sums of the first 7 primes? Wolfram alpha. I think we did this before. Sum of first 7 primes. Was it 129? Oh no, I think we did. We did a different number there. All primes between the first one and the 7th one, 58. So obviously we've got a bug here. Let me fire up GDB on my program. Okay. It's a command line interface. The GDB calls it actually a TUI. That's a text user interface. And so I can just start giving it commands. I can tell it, run the program. All right, it did. It ran the entire program all the way through, displayed the total of 7. Obviously, there's a bug in it. So the first thing I want to do is I want to see my code. Layout next does that. Now, it's not running right now, but it will show me the code once it starts running. A.out. Run, sorry. Run. All right, there you go. It showed, now it exited normally. Again, it's printing this total of 7. That's way too fast, right? I can't look at the values and try to diagnose what's going on. So what I want to do is I want it to stop. I'm going to set a, oh, by the way, sometimes it screws up. You can always go refresh, and it refreshes it for you, right? Okay, let me go ahead and make it bigger too. Move it up, and there we go. All right, so I want to run it, but I want to run it line by line. So what I'm going to do is I'm going to set a breakpoint. A good breakpoint for this would be to set it at main, at the beginning of the program. Break at main, run. Right? And now, again, refresh if it screws up. There we go. I'm on line 15. I can now step through my program line by line by either typing next, 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 right? Or since that's such a common command, simply just N will get me to the next, 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 next. Right? All right, at this point in my program, I should have set all of those values in that array. How do I know? Let's just make sure, though. Let's print primes. Right? That's a memory location. Why? Because primes is a pointer. All right, well, I want to know the contents of that array. So print dereference it, primes. It gives me the first one. I want them all. So print primes. How many are there? 7. At 7, it'll print the entire thing for me. 2, 3, 5, 7, 11, 13, 7. OK, this all looks right, right? So what's going on here? Let me go next. Right? And I'm now at this point. It didn't go into that function for me yet. So let's print s. Well, obviously 7. So my input is correct, but my output from that function, that sum function, was wrong. So let me go ahead and set another breakpoint. Clear main. Clear takes away a breakpoint so that it will no longer stop at the beginning of the program. Let me go ahead and set another breakpoint in sum. And then we'll run the program. And it's already running, so it's going to ask me, do you want to restart it? And yes, I do. Refresh. So if you notice, it went through all of these lines in main until it got to this. And then when it went into the sum function here, then it started executing. So I want to look at the values that I received, say. Print, what is it, ARR? ARR at, and then 7. OK, I received the input correctly. Did I receive n correctly? Yeah, 7. OK. What about the values of I and total so far? Print I. OK, 0. Print total. 0. OK, maybe. Although it's not manifesting itself as a bug, what should I have done here? I should have initialized it to 0. I'm just getting lucky here that it is initialized to 0. All right, so let's go through this loop. All right, next, next, print I. So I is still 0 because it's at the end of the loop, but print total, and it's 2. So it added that first prime, right? Remember that the primes 2, 3, 5, 7, etc. All right, so the first iteration was fine. Next, next, print total. OK, so 5, 2 plus 3, 5. Everything looks OK so far. I don't like printing all that stuff out. So let me go ahead and watch a variable, total. Now, anytime total changes, it'll tell me automatically without me having to print it out. Next, next. It went from 5 to 10. 2 plus 3 plus 5, 10 so far. So far, so good. What's the next value I should expect? 17. What's the next value I should expect? What's the next? 7, then 13? Oh, no, 11. So 28, right? There we go. Then 13. 13 should be 41. OK, then 17. 41 plus 17 should be 58. All right, so what's the deal here? We're getting the correct value here, but the main function's not receiving the correct value. Right? What is it? Finish. I'm going to go ahead and finish out the execution of this function and see what it returns. Its return value is 7. Why? What do you see around here now? Yeah. The total is a scoped variable, right? And so it has a value of 58 at the end of that function, but what do I do with it? I don't return it, right? And so the return value here is some mysterious value 7, right? All right, I found my first bug. I don't have a return statement here. Quit out of GDB, go back into array program, fix it, return total. There we go. And move on. Then GCC it again. Let's run it. OK, now the total is 58. Right? So I was able to find all of that by running it through GDB, running it line by line, being able to view all this stuff. Some other things, I think I covered everything here, but layout next allows you to see your code. Next, or N for shorthand. You can print individual variables, or you can print an entire array by dereferencing it and then telling it how big you expect it to be. You can set a breakpoint either at a function or at a line number. If you go 25, then you can set it at a line number. If you have multiple source files, then you can specify source file, colon, and a line number within that source file. You can continue execution of the program. You can watch variables and see how they change, et cetera, et cetera. Now, this is only the tip of the iceberg here. GDB allows you to do a lot of other things. A lot of things that you can't normally do by just running a program and doing a bunch of print statements. Right? Again, that's poor man's debugging. I thought that there were 2 bugs in here. Let me double check. There is a problem here, but it's not necessarily apparent. Between these 2 lines, are these 2 lines correct? I declare my pointer. I call malloc, but what did I forget to do? What should it have been? Equals. Right? Malloc returns a pointer, and of course I should then int star it. Right? Let me show you very, very quickly here 2 other tools. Right? This is not going to take long. First of all, if I have been using my own advice this entire time and using wall, let me go ahead and go back down here. If I had not had this return statement, let me go ahead and get rid of that, put my bug back in there. If I had just simply used wall, array program, I wouldn't have needed to do any of that stuff. What is it telling me right there? Line 38, control reaches an end of a non-void function, but I haven't returned anything. There's a big red flag right there. Take care of that warning. There's another big red flag here. Warning, primes is uninitialized in this function. Right? That was the second bug. Primes is just a dangling pointer here pointing to what? Well, it just happened to be pointing to memory that belonged to me, so great, I got away with it. But that's only because I only put in 7 integers here. It was small enough that I didn't corrupt my own memory and I didn't cause a segmentation fault. But using GCC as a linter, which hopefully everybody is doing now, and if not, then you should be doing this, would draw attention to those 2 things right there. Another way that you can do this, GCCG, array program, is somebody asked last week about, well, is there a way that you can detect memory leaks and stuff like that? And there is a limited way, valgrind, right? A.out. Oops. Valgrind. I'm on CSE, right? Let me see. What are the commands? Oh, there we go. A.out. There we go. There. So, lots of cryptic stuff. This is a more advanced tool. It's a dynamic analysis tool. Basically, it runs your program and checks for common problems. Memory leaks, it can catch a lot of memory leaks. What did it catch here? Use of uninitialized value of size 8 on line 18. What did it catch? It caught me using primes when I had not initialized it to anything. And it caught me doing that many, many, many times. Right? Each one of those lines is a problem because I set it equal to 2. I set the next one equal to 3, ... Each one of those uninitializing things. You can also catch things like, here, let's go ahead and put in another bug here. Let's say char name. There we go. And then name sub 0 is equal to C. All right? And then printf name is equal to %s. What am I forgetting to do here? There's no guarantee on what's stored in here. I just put in a C. Is that the end? I could put in the full thing if you really want to. Name of 1 is equal to h. There are a couple of things here that are wrong. First of all, did I specify a value here? Nope. All right, fine, 10. That's the first thing that's wrong, and now it's fixed. But have I ended the string? How do you end a string? With the null terminating character, names of, I don't know, 2 is equal to the null terminating character, right? So that's correct. If I don't do that, does valgrind catch it? And go up to valgrind, run it. There we go. And up above, ooh, yep, it caught it. Conditional jump or move depends on uninitialized values. When I try to print it from main on line 18, oh, that's a whole bunch of wrong right there. Now, the rest of this stuff is not our problem. Printf is actually calling a bunch of other functions that are part of the system. There's no way that I can go in and start mucking around with the system code. But I can look at this as a stack trace. It's showing me that main called printf called this function called this function, this call is right, the call stack. The thing that I do have control over, though, is array program line 18. Right? That's where I need to be looking for my problems. Those other library functions, those other system libraries, very, very rarely will they have bugs in them. And those types of bugs are way beyond the scope of this course. You'd have to be like a top contributor to the Linux development ecosystem to be able to even look at that code. So, I mean, it's open source. You can look at it if you want to, but be able to understand what's going on there. So there is obviously something wrong with line 18, and it is that move depends on uninitialized bytes, right? And it also caught all the other stuff I was doing. If you're interested in valgrind, you can go ahead and run it on your lab 7 from last week. We demonstrated a memory leak, and it would allocate memory for an array, and then lose its reference to it. Then do it again, over and over again. You are using more and more and more memory. Valgrind, if you ran it through valgrind, it would tell you exactly that there's a memory leak on this line. You initialized something that were here, but you never cleaned it up. And so it can't predict where you should have cleaned it up, but it can definitely tell you that it was lost, that it's a memory leak. And this is a dynamic analysis tool. It's not a debugger, but it will give you hints as to what's wrong. But if you want to use it, go ahead. It's installed on CSE. So 3 great tools to use when you've got a problem, when you've got a segmentation fault. Always use wall. Then you can run it through a debugger, or you can run it through valgrind to get some hints as to what might be wrong. Right? Any questions? All right, then when we come back on Wednesday, I will bring last semester's midterm, and we'll do it together. I'll even post it if you want.